I tried. I did my best, okay? There's only so many jokes you can make on relativity, and one of them is things taking a lot of time. Okay, welcome everybody. Second week of relativity. Just with a show of hands, how many people are getting used to the strange world of relativity? And we first have to define what do I mean by the word getting used to. Let me sort of ask the opposite questions. How many of you have some confusion on the things that happen in relativity? Don't be shy, because it is a difficult course. Okay, it's a difficult subject. So I saw about 3/4 of people raising their hands, and I wonder where confusion lies. So let's start with a little bit of interaction. By the way, if you are confused, you're very right. That has to do with two reasons. One of them is that it is just a confusing world. Okay? No, I mean, it really is as simple as that. You have lived for 18, 19, 20 years or so thinking that time and length are absolute values, that those things are invariants, the amount of time and the amount of distance. What is one thing that we have learned in relativity is that the amount of time and the amount of distance is not invariant. Sure, I mean, it takes an enormous amount of velocity before you see these effects happen, and this exactly is why you're not used to this. You've walked this earth for all this time not thinking about this and not having encountered this, let alone having to think about it. Okay, so it really is just in large part a matter of getting used to these rules that nature apparently obeys, and that takes time. There's no joke there. I mean, it literally takes a certain amount of time before you understand and are capable of working with that. That was one reason. There's a second reason that things are confusing in relativity, and that is that because we haven't done all of it yet. There's parts that are missing, and today I'm going to fill in a couple of missing parts. I got some emails from people where they said, well, I did this calculation and I found that if you do it like this, I get this number, and if I do it like that, I should get the same number. I get a very different number. Okay? That is because there's parts of it still missing, and that's what I'm going to fill in today. Now, rest assured, everything that we've done so far is entirely correct. So if you've understood everything from last week, you're perfectly on track. So let's fill in some details today. Gonna just a little bit of interaction here where people have confusion. I cannot promise that I can give you one sentence resolution to your confusion, but I just want to know if there is confusion, where does it lie? I saw 3/4 people saying, well, I don't understand everything yet. Yet at the moment that I ask, so where's the confusion? All of a sudden people say, oh, well, no, I'm fine, I understand everything.
When we changed the events, I have always difficulty, like when it's not like implicitly, like very explicitly said, oh, now we changed it, it's that.
Yes.
To make the change like spontaneously, or like to know when to make the change.
Yes. And I think people share this, yes? With both tutorial groups last Friday, we saw that there was at least one exercise where all of a sudden you had to switch events in order to do your calculation correctly. And it is so subtle that you would almost miss it if you don't pay attention. Now, one of the things that I told you on Friday was that is one of the very first things that you have to do if you do your calculations in special relativity is really be sure what two events you're looking at. Otherwise things will go wrong. Any more confusions? Yes?
When last Friday we were talking about a proton crossing the galaxy.
Yes.
When we're stationary, we see the beam of light passing.
Yes.
We see the distance covered by smaller than it actually is because it's going so quick. Yet when we try and solve it, you said, okay, let's hold that the photon itself is stationary and the universe is moving towards it.
The proton wasn't a photon, but yes.
Right.
Okay, yes.
It is moving towards it in the opposite direction at that speed, so it sees the distance contracted.
Yes.
Can you not solve it otherwise? Like, because why would you hold the proton stationary and then see the thing moving?
You can do it from both frames. For one frame, you have to invoke time dilation. From the other frame, you have to invoke Lorentz Construction. Both of them will give you the same answer.
Okay.
So here again, it comes back to deciding what two events are you looking at. If you've discovered what two events you're looking at, you can also pick out who of the two observers, if any, in your case the proton and or the galaxy, see the two events happen at the same location. If you figure that out, then you know if you're allowed to apply time dilation. If not, you can go to the other guy's frame and apply Lorentz Construction.
It's one or the other.
It's one or the other, yeah. You cannot have one observer applying both. Any more? Because there is one by Michaelis that I really want to share with you. And if not, I'm going to take that one. Can you share what it was? Because it is very important.
Let me just remember.
Yes.
So, for example, we have a spaceship.
Spaceship.
We have the Earth. And the event is that the spaceship is leaving, the one event that the spaceship is leaving the Earth, and the other is when it arrives, like far away from the Earth.
Okay, so let's make it explicit. So you have Earth here. Over here you have some other place in the universe. Spaceship leaves here, goes over there.
Mm-hmm.
Okay, yes?
So you take the two reference frames, one on the Earth and one on the spaceship.
Mm-hmm.
And you have on the spaceship the reference frame, the two events happen in the same location, so the spaceship takes the gamma.
Yes.
So, for example, if the spaceship takes 10 years to go the distance, then from the Earth you're gonna see the spaceship taking like millions of years.
Mm-hmm.
If the spaceship is going very close to the speed of light.
Yes.
So, but if you like look the event in the other way, like if you're on the spaceship and you want to see what happens to the Earth, then, for example, the event is that the Earth is close to you, and then when the spaceship is far away, you see the event the Earth very far.
Mm-hmm.
So the Earth has a velocity very close to the speed of light, and then the Earth takes the gamma.
Yes.
If you take two reference frames again, and I think that has like different results.
Yes, no, that gives very different results. The question that he's asking is, well, we know who gets gammas, yes? I mean, it's always the person who measures time at one and the same location. The both events measure at the same location. But you can set up situations where it looks as if both observers are allowed to place a gamma in front of his or her amount of time.
Mm-hmm.
So that means that one of the other person will say, well, you take my time, multiply by gamma, you get your time, whereas the other says, no, you take my time, multiply by gamma, and get your time. And gammas make amounts of time bigger, yes? So how can one guy say of the other, your time has to be bigger, whereas this guy says, no, your time has to be bigger? That is a huge paradox. Okay. Whatever situation you encounter this in, because you encounter this very often, this is called the twin paradox, or a variation of the twin paradox. Now, you know, paradoxes are part of next week, but I think that this one is so important that let me at the very least say where the difficulty lies. All right. So I'm going to take your situation, but I'm going to make it a little bit different to put it in more context with the usual standard books that you see in these things. It's called the twin paradox because you have a twin, or twins, so you have two people. One stays on Earth, and the other decides to have a spaceship and go this very big distance away. And this guy is traveling. And then the person who stays at Earth says, oh, wait a minute, you have to take that person's time, multiply it with gamma, and then you get the amount of time that I think that person took to take the trip, yes? And you end up with a number. And if you do the calculation correctly, you will find that person has not aged as much as the person over here. Why? Because there was more time. The gamma that this person's time gets makes my time a bigger number. So that means when I look at that person, I say that it has taken longer for that person to reach her next birthday. That's not a way of saying that that person will go in slow motion. So I look at the other person and say, well, look, that person is getting younger than me. Or not younger, that person is getting slightly less fast old. Does it make sense?
Yes.
Okay, because nobody gets younger in relativity, okay? You can only get old at a slower pace. Whereas this person, while traveling, could say, no, wait a minute. In my reference frame, it's the Earth moving in that direction with a high velocity. So that means I can take that person's gamma, that person's time, multiply it, and I can calculate how much more time that person has done, yes? And I end up with the same amount of less getting old of that person. So both will say that the other person has gotten younger. Well, not younger, has gotten less old. I have to be careful with my language here. Now that is a paradox, because who of the two is actually getting old faster? That is a huge paradox. That is your paradox. That is what you are saying. Now this one is so important that I feel that I should stress it. Does anyone, by the way, happen to know? Because it's a well-known paradox.
You told about it like in last lecture. You said it was something to see with acceleration, and that was.
Yes,
What
that is
breaks
right.
the symmetry, right?
There's something that breaks the symmetry here.
But then Earth, like if we look at another point, also Earth is also was also moving at one point. So I mean, we can also say that Earth was at one point accelerated.
Okay.
If we just like. If it's just like the explanation is acceleration, like if I...
Yes, but acceleration is a little bit different than just velocity.
Yeah, but like if it's, for example, if it spins,
yes,
there is an acceleration, no?
Agreed, yes.
So then we can also say, okay, which one is like...
I will tell the answer, because the question is fully clear. I hope the question is clear to everybody, that there's an issue here. And it harks back to the question, why do we call this particular version of relativity theory special relativity? There's one misconception about special relativity, and that is that you're only allowed to apply it when you're looking at things that go with constant velocity. This is sometimes you read a book. Oh, special relativity is about constant velocities. Now this is wrong. You can apply special relativity to accelerating things. In fact, last week when we were here, we had this time dilation formula. Let me write it down one more time. That dt is gamma d tau, where d tau you now recognize as the amount of time for the person who sees two events happen at the same location, the eigentime or the proper time. And then we discussed, but what if gamma, which is a function of v, what if v is not a constant? And I said, no, that's fine, just integrate it. Because by good approximation, an accelerated motion is just really small chunks of constant velocity. Just every chunk has a slightly bigger constant velocity. Okay, and adding small amounts, small chunks together, while it increases, is literally what you call integrating. This is what integrating is. So you can very much apply special relativity to cases where things are accelerating. So you can have an accelerating proton, or you can have an accelerating spaceship. It still works. Then where does this whole idea come from that special relativity could not be applied for accelerated motion? And here's a very subtle point, and that's exactly where the resolution of this problem lies. Namely, you're allowed to view things that go in an accelerated fashion as long as you yourself do not accelerate. Okay? There's a very subtle but extremely important difference between these two statements. As long as you stay in a frame, a reference frame, that itself is not accelerating, then you are allowed to apply special relativity, even if the other guy is in an accelerated frame. You are not allowed to use special relativity if you yourself are in an accelerated frame.
But relative to what?
And that is a very good question. And I think that was also your question. Or no, excuse me, that was yours. Relative to what? Because, by the way, thank you for putting the word relativity in your question. This is why it's called relativity. You only compare it to something else, yes? Relative to what? Because you could say, well, wait a minute, if this guy is accelerating with respect to that guy, then the other guy might well say, no, it's the other guy that's accelerating, right? That is not true. And that is because nature has built in a difference between acceleration and non-acceleration. And that is something you cannot do away with going to some other guy's frame. Do you know what the difference is? It's not even a relativity. Sorry?
Free falling?
Oh wait, that's very interesting. Could you continue the thought, please?
Yeah, so if you are free falling, you're the true inertial frame.
I heard the word inertial frame.
You're not anymore on an inertial frame.
That is exactly the right answer. And if people don't know the words, let me re-emphasize, it's the correct answer. So let me retell that story. Let's go to classical mechanics. Forget for the moment about relativity. Okay? Just classical mechanics. And suppose that you have Newton's second law that all of us know, yes? Here's Newton's second law. And if you're really cool, then you know that it's really another way of saying dp dt, change of momentum. Okay? Question. Are you allowed to use this law in all situations? So you say no, but what is the no here?
Only on inertia and reference frames.
Yeah. And that is that your answer as well? Yeah. Okay, only inertial frames? What is an inertial frame?
It's not accelerating.
With respect to what? Then I'm going to just give you back her question.
With respect to the initial
To?
in the initial location.
Yes, but then you would already have to have identified the other inertial frame.
There's no
Maybe a way
resulting
to
force.
know if we are inertial is just like when we drop a ball. If we see that it falls in a straight line, we know that it's an inertial reference frame. If we saw that from the point when the point where it's supposed to fall is a bit like further away than what it should be, then it means that we are in a like an accelerated referential frame. Like, I mean, if we have just like in a place when we like just in a, like, I don't know, an elevator and don't see anything.
Yes.
If we just drop the ball and you're not moving, I mean, let's just say the elevator moved that way. If the ball falls directly in the same like axis, then we can say that, oh, there is no acceleration in respect of the perpendicular axis. And if otherwise, if the ball, like if we are moving, so we are in the elevator and I drop my ball here, and we are moving with an acceleration to that in that way, then
I see. Okay.
Likely, that could be a.
That's interesting because
there is another force that is applied than the simple.
Okay.
Like.
Yes, you are very right, and the interesting thing is that you already built in gravity here, right? Because you use free fall. In fact, that's also what you used. So gravity is, in some way, you can tell whether you are in the right frame to use Newton's laws. Now that is very deep waters. In fact, I start my general relativity course by going exactly there. So I'm going to say the same thing, but I'm going to leave gravity out for the moment, even though both of you were right. Okay. I was expecting when I asked the question, can you always apply Newton's second law? The people would say, no, not in quantum mechanics. True. And not if you maybe go very fast, because there are some people who say that mass all of a sudden increases if you go very fast. That is not true. We will see that in lecture 5. Okay. But even if you stay within classical mechanics, you don't go very fast, so you have to use relativity, and you don't look at very small objects, so you have to use quantum mechanics. Even if you just stay in the realm of normal classical mechanics, then still this law you cannot always use. And you only have to look at the one time that you sat in that plane and the plane started accelerating, right? You're on the runway before it goes up. You feel yourself pressed in your chair behind you. That is very interesting, because there's no force operating on you, is there? What is happening, there is a force maybe that's pushing the plane forward, but there's nothing pushing you forward. Well, ultimately the chair will help you push you forward, but at the beginning of this accelerated motion, there's nothing pushing you forward in principle. Agreed? And that's exactly what you see, because then your inertia tells you that your mass wants to stay at one position where it was. Whereas in the meantime, the plane underneath you is trying to push itself forward. This is why you feel yourself pressed in your chair. Here's a very good question. If you didn't know you were on a plane, you just happened to be in an accelerating frame, and you wanted to know if you were in an accelerated frame, in that accelerated frame, if you would apply Newton's second law to your own motion, you would get the wrong answers. Agreed?
Yeah.
Because you would say, hey, there's no force operating on me. There's no force, yet I feel an acceleration backward. So apparently, Newton's second law does not hold in the airplane frame. Now it does hold in the ground frame in this particular case. There it would hold, but it would not hold in the airplane frame. So what I want to convey to you here is that there are frames in which Newton's second law simply will give you wrong answers. Now in case of the plane, it's very easy to see whether you are allowed to use Newton's second law. You just look out the window and see, oh wait, I'm the accelerating guy. Okay?
Yeah, but
yes.
in Newton laws we defined inertial like referential.
Yes.
Like in relativity we just like say that it's just depending on what we are looking. So there is no like absolute reference frame.
No.
It's just like a.
And that is still true. But I'm making a more subtle point here. What I'm saying is, before we go into relativity, I'm still just in classical mechanics. Nature has chosen that there are reference frames in which you can apply Newton's second law, and there are reference frames in which you cannot. Okay? And that means that if you're going to apply classical mechanics, again, forget about quantum mechanics or special relativity. If you're going to apply just normal classical mechanics to your problem, to your situation, you first have to find out whether you are in the frame where this law holds in the first place. Now, by definition, this is called an inertial frame. The inertial frame is a frame which Newton's second law holds. This is not a man-made creation. Nature actually cares whether you are in an inertial frame or not. Nature has decided that there are two types of frames. You're either in an inertial frame or you're not. Now, how do you find out whether you are in an inertial frame? Yes.
Let's pretend we just apply a force. If
Yes.
it changes depending of direction,
Aha.
then if there is a subtle change, if we apply the force, for example, that way or that way,
Yes.
and if it changes, it varies depending on the direction,
Yes.
then there is we are probably in an
That is a very good point. That is a very good point. What you could do, and I think I'm going to say exactly what you say. What you could do, I want to know whether I'm in an inertial frame. In other words, whether I'm in a frame where I can apply this law. What I could do, and I think this is what you're saying, is just throw some rocks around. Okay. If I know with what force I push the thing, I just calculate how it should have gone according to Newton's second law, and I make sure that I make no mistakes, right? No errors in my calculation. I check if the thing actually flew the way that Newton's second law predicted. If not, then apparently the rule doesn't hold. I'm not in an inertial frame. Agreed? This was
or with spring, for example.
Or with a spring, that's fine too. I mean,
it's just like
no, you make sure that you push against that something pushes against something else. You calculate this. If it doesn't work, apparently you're not in an inertial frame.
But
yes,
just a question. If, for example, we must also have a sense of direction. We must try every direction because, for example,
Good
if
point.
we have a
Yes.
force that is perpendicular and I
Yes.
push it that way, the force in that way will give me the prediction if I just look.
very true. Suppose that the inertial frame, the correct inertial frame was this frame, and accelerating it that way, then throwing pens this way will
Yeah.
not reveal this. Yes, so we should do it 360. And if at some point we find something that doesn't hold, we're not in an inertial frame. Okay. Here is a subtlety, and I think Ash is going to say it.
Yeah, well,
Go.
for the thing to fall down, you need some other force to be applied on it, right?
There we go.
What if you're like somewhere in the middle of two galaxies and there's like...
No, then it would still work. I mean, you could take your spring, right? And
No, like what if you're just like, just you there with the ball?
yes,
You throw it and then it just like flies away from you.
yes, but at least you can calculate how far it flies with respect to you.
Then you'll fly away as well, right?
And that is true. You have Newton's third law that makes life difficult because you have no idea whether you're being pushed back by the thing. That's true. Oh,
That's why I was
Yes.
thinking of it. Just let's say we have a spring and we need a very precise force to be able to push it.
yes,
If I'm in one direction, I'm unable to push it, or it's way easier to push it than what
Yes.
I usually add. So if it's fixed,
mm.
then I would be say, oh, okay, in that direction, when I'm pushing in that direction, it makes it way easier than when I'm just doing like, I don't know.
No, that
pushing
would probably that would probably solve his problem as well, right? Because if you would push in different directions, then at the very least you would know of that particular frame in which you were, your ball in space. If you throw it this way, it would operate differently if you threw it that way.
At
Even
least
with Newton's third law taken into place. So that's correct. But here comes a subtlety. Right? We're still in classical mechanics, no relativity just yet. But I will come to the Mercatus' original problem because it's extremely related to what we're talking about now, but still classical mechanics. Here's the thing. So we now have a way to find out whether we are in an inertial frame. You just throw some stuff around, and yes, maybe 360 degrees, right? And we check whether this law holds. If it doesn't hold, and we haven't made any mistakes, and we haven't made any mistakes in our calculation and or our measurement, etc., then we can conclude if it doesn't hold, we're not in an inertial frame. Fine. Okay, but here's the crappy thing. You mentioned the spring. You said, well, just throw something away with the spring.
I was just like thinking of the force I need to apply.
I know, that's Hooke's law, I know. But here's the thing. In order to calculate whether the thing flew the way that you expected it to fly, you must have known what the force was with the spring pushed it away, or with which I pushed it away, or whatever thing you're going to use to do the pushing. Okay, could be electromagnetism, could be a spring, could be my muscles, could be whatever. I need to have known what this number is. Now, how do you find this number?
With spring.
But no, how?
Yeah,
How?
but then if we, for example, there
Yes.
is a spring that I just can barely, I cannot stretch it in the
Yes.
normal condition. The
Yes.
only condition if it's I get help of a non-inertial, let's say, system. So in every condition, I'm
Yes.
never able to spring it. There is just one moment when I know that, oh, I'm able to push it. And when I'm able to push it, then I'll be, oh, okay, that's the, let's say, we are in a non-inertial frame, and I know that it goes in that direction because it's only in that direction that I'm able to push the spring, whereas I don't have normally enough force, let's say, to be able to.
Yes, but in order to know how much it pushes back, you need to know how much back pushing the thing does.
I'm just saying it's a qualitative point of view. I don't know how much, but I know that this time I could do it. Whereas all the other time I wasn't able like to press it because it needed like too much force, for example.
I think I agree with you, but not entirely.
It's just like.
Let me think about it for a while. Let me go back to my point. There is something there, but there is still an issue. But let's go back to the simpler point for a moment. In order to do my check whether I am in an inertial frame or not, right? Throw some rocks around. I need to have known what this number was. I need to have already known how much. Let's take the spring example. How much the spring has pushed. Question: how do you get that number? And you can't say, well, we just call it a factory where they built a spring and they gave me the number, because the only way to know how much something has pushed, we don't have a pushing meter, but the only thing that we have is, well, if you know how much something accelerated, you can calculate back how much the force was. But that gives us circular reasoning, because in order to do our experiment to find out whether we are in an inertial frame, right? We throw some rocks around knowing what the force was. We must have already known the force, but in order to know the force, we must have already thrown some stuff around knowing that we are in an inertial frame. The very important point here is you cannot do this test of throwing around with rocks to see whether you're in an inertial frame if you don't know what this number is, and the only way to find this number is to first go into an inertial frame, then measure acceleration, then calculate back what F was. So whatever you do, you always end up back to the same question. I am not sure whether I'm in an inertial frame.
Then I don't. I think if I just took a spring and I see that under normal circumstances, here I don't want to know the acceleration. I just want to know if I'm in an inertial or non-inertial thing. So this time it's just like I'm pushing with my two hands. Normally I don't have enough strength to be able to compress it.
Okay, there you go.
And then if I am in a certain...
No, I'm stopping you here. Normally, what is normally, was that when you were in an inertial frame or not?
Or let's say that when I press it in that direction, I'm unable to compress it.
In what frame?
Whatever, even if I'm in the cabin, let's say I'm just unable to do it at one point. I'm unable to press it, unable to press it that way. But when I turn it in another direction, then I'm able to like compress it. Then I know that I'm not in a referential frame. Even if I don't know the force at the beginning, I notice a difference.
No, it doesn't tell you anything, because you could have also been accelerating in whatever...
Yeah, but if I'm accelerating, for example, in that direction, let's say we have a force that is going in that direction.
Yes.
So only when I'm in that direction, I see that I'm able to compress it. So I'm able to notice a difference than when I'm in this direction, when I'm unable to like... I don't know if I won't be able to say like qualitatively, quantitatively where or how I'm moving, but I can just say, oh, I'm not in a referential frame, or I am.
Okay, but I think you're giving the conclusion away that I wanted to draw, because I think you and I are going to say the same thing. Okay, so let me do this story, and you tell me whether this disagrees. Okay. My point here is, and I was being quantitative, in order to do this experiment, you need to know how much force you did the pushing with. How do you find the amount of force that you're pushing with? By measuring the acceleration and then calculating back what F was. But that force, that only works if you were already in inertial frames. You're in a loop here. And Newton, as in the scientist, was very much aware of that. He saw, wait a minute, how do I find out whether I'm in this preferred system or this non-preferred system? And the only way to find that out is not by Newton's second law itself. So he said there needs to be some other law that tells me whether I'm allowed to use Newton's second law. Now can you guess what law that was? That was the first law.
Moving speed, constant.
Yes.
Speed.
Newton's first law is typically stated as, well, if you don't push against anything, that means it will have a constant velocity, or when it is at rest, it will stay at rest. It's called the law of inertia. Okay. Now, some people, and unfortunately I have to say some teachers even, say, well, Newton's first law is only a special case of Newton's second law. Right? Here's Newton's second law, and if you don't do any pushing, F is 0, then acceleration is 0, therefore constant velocity. So it's really just a special case of a bigger law. This is wrong. I actually saw it in a high school book at some point. Prove that Newton's first law is only a special case of Newton's second law. Now, if it was, you never needed the first law in the first place. Okay. The thing is, Newton's first law is the law that tells you whether you are in an inertial frame or not. If you go back to your airplane situation, how can you find out whether you are that the plane is a non-inertial frame? You take something, you make sure that there's no forces acting, there's no springs acting on it. So you don't have the issue that you first have to find out how big the spring is pushing against things. You just make sure that nothing is pushing against the thing. If in that situation the thing will still spontaneously accelerate, then you conclude, wait a minute, Newton's first law is broken, therefore I'm not in an inertial frame and I cannot use Newton's second law. Do we all see this? Mm-hmm. It's extremely important. Newton's first law is the big test that tells you whether Newton's second law is allowed to be used in that particular frame. It's not a special case of the first one. It tells you, it's a check whether the second one can be allowed. It can be used.
So it's just like if the idea is just the same. The
yes.
spring like press almost
yes.
spontaneously. Let's say.
Exactly, and this is why it took me a while to get there. But this is why I realized you and I are saying the same thing.
That force plus the spontaneous thing to be able to compress.
Exactly. So what you were really doing with your spring example was
it doesn't move until like.
Exactly. So you were applying in a different way than I envisioned. So it took me a while to understand what you were saying, but you were applying exactly my point. So for everybody, please, the first law is a test whether the second law applies. Now, I wanted to convey to you the importance of knowing whether you are in an inertial frame or not. This was all classical mechanics. Now let's go back to relativity. Because, yes?
Sorry, could you redefine inertial frames?
Yes, an inertial frame is a frame in which Newton's second law holds.
Well, okay.
So that's it, really.
So a resultant force would cause an acceleration?
Yes, by this amount, yes. Now, going back now to relativity. And this was originally Michaelis' question. His question was, but remember the twin paradox? Who is the person who is allowed to say that the other person has gotten younger? Not gotten younger, I keep on saying it the wrong way. You know exactly what I mean, right? Has gotten less old. Okay. Special relativity only applies for observers who are in an inertial frame. You're allowed to look at things that accelerate as long as you yourself stay within an inertial frame. If you leave an inertial frame, you're not allowed to use any special relativity anymore. That is the big thing about inertial frames. It's not just a test whether you can use Newton's second law, it's also a test that tells you whether you are allowed to use special relativity, or if you don't, you have to go to general relativity. Now, just a second. We are by construction in this whole course just going to stick to observers being in inertial frames. So that means everything we're going to do, you are allowed to use special relativity. You're allowed to look at things that accelerate, but if you yourself are in non-inertial, how do you find out? Well, not by checking whether you accelerate with respect to somebody else. If you have two people and they're accelerating with respect to each other, and you want to find out who of the two is in an inertial frame, ask both of them to check whether Newton's first law holds in their frames. The person for whom it does not hold is not an inertial frame. That person is not allowed to use special relativity, and the other one is.
For example of the ship, even if it moves at a constant speed.
Yes.
But then it's no more an acceleration if it moves at a constant speed. No?
Then
we still have the problem.
Yes, I agree. But you're going back to your to the twin paradox again. But now you're saying, well, suppose that both of them are
moving at the same speed.
Constant velocity. Yeah. Agreed. Okay. Then there is the loss of simultaneity that we're going to talk about today. There was one of the two tutorial groups that I sort of gave a little bit away this whole issue, that there were two ways that you can solve a paradox like this. Right? The paradox was, well, who gets to say that the other one has gotten less old? And now, I hope that you now see the answer. Because one of the two, when he applied special relativity, placed a gamma in front of his time to calculate the other person's time. One of them was not allowed to use it in the first place. Who was that person? The person for whom Newton's first law did not hold. Mm-hmm. And that breaks the symmetry. Then all of a sudden, one of the two, it was simply wrong in their calculation. Now, in our case with the twins, with one person here and the other one being sent away, sending away means that at the very least somebody must have accelerated, yes? Yeah. Somebody was not in an inertial frame.
Oh, okay.
You find out who that was. How do you do that? Apply Newton's first law. The person for whom Newton's first law holds was in an inertial frame. That person can use special relativity. The other person cannot. And then you have no symmetry anymore. You cannot say, well, both of them get a gamma, because one of them never got a gamma because he was not allowed to use special relativity.
So we have to check before.
Yes.
Just we cannot check like wait 10 minutes and
Nope.
it has to reach a constant
Nope.
speed. We have to check the moment it
Yes,
starts to.
exactly.
Okay.
This is why Newton's first law is the first of all these laws. It's the. I mean, if you have never done this check, you're not allowed. You don't know whether you can use Newton's second law. You don't know whether you can use special relativity or general relativity. This is the very first thing that you check whether you are in an inertial system. Now you don't have to do this check in this course because by construction we're going to stick to inertial systems. So one more time, I will be there in a second. One more time. Special relativity you can apply if you are in an inertial system, even if you look at things that accelerate. Okay? That's all there is. If you want to know, well, what should I do if I am not in an inertial system, this is why you have general relativity. But
Okay,
we're not-
so the guy in
yes.
the ship couldn't, like, because he had to accelerate at one point just
Yes.
to start to fly,
Exactly.
even if now he's in a
Exactly.
normal Newton
Exactly.
thing, couldn't, like, measure, we cannot apply the gamma thing, like, from
Exactly.
his point of view.
Exactly.
Okay.
And your point was, well, the person is accelerating, or even if at some point he's going with a constant velocity, somewhere in his journey, somebody did an acceleration, okay? So somebody at some point has broken Newton's first law.
Yeah.
And that's all.
Yes.
Yes. Oh, no.
No.
Yeah? Okay. Yes.
Yeah, remember like the 410 when there was the star exploded while the ship was traveling?
Yes.
And as I remember, what we did is we applied it in such a way that the ship's time was slower than
Yes.
the sun's times. Isn't that breaking this?
No.
But the ship was accelerating.
Um,
It's like the same as applying the thing to the twin. That's
I don't think we considered the acceleration.
no, the acceleration in the exercises is kept out.
Oh, okay.
Okay, that's very artificial because of course somebody did some acceleration at some point,
Yeah.
but they're leaving it out, which is again
And
not physical.
What
so
is
we need prior knowledge for every exercise to know which one has accelerated.
Yes.
At one point, someone must say, because if we
Yes.
just say, oh, there is two moving objects, like in respect to one another, like it must at one point someone must tell
Agreed.
us, oh, that one has like
Agreed.
accelerated.
So that means that all of our exercise is going to be extremely artificial because if you have people moving with respect to each other, then somebody did an acceleration at some point. Okay.
And it's not always mentioned. in the exercise.
No, it's never mentioned in the exercises that we're going to do. That means that the amount of non-inertialness becomes smaller if the acceleration only took a small amount of time.
Mhm.
So that means that they just sweep it under the rug.
Okay.
Okay. Now, so again, long story short, inertial frames. That solves your symmetry issue. Who gets the gamma? Who gets to say whether the other person got less old? Okay. That's one. And then there's a second thing, and that is the simultaneity thing, which is topic of today. Yes.
What if you start accelerating around the Earth, like on the surface,
Yes. What about it?
and get to the like around the speed of light?
Yes. Then somebody did an acceleration, agreed? Because moving in a circle is also a type of acceleration. Not in velocity, but in direction.
Yeah, but then both of them are kind of in the Earth frame.
No.
Earth is not inertial.
Because the person in the guy flying around the sun, around the Earth is not an inertial frame. He's accelerating. If you want to find out why, ask the guy to drop a ball.
But
It will land behind him.
Excuse me.
Okay, what if he's not flying? If he's on the Earth's surface, will
Yes.
the Earth's surface shrink for him?
No, because now you're again applying special relativity. You're taking the length that the.
Or I mean, for the other guy, for the guy that's looking.
No, that is true. Yes.
I have another last question.
Okay, but then I'm going to move on because
Then-
we're really deep already in the territory of next week, namely.
But it should be impossible then to have it's purely theoretical, pure inertial like system, because
Yes.
even Earth isn't inertial because it spins, so it
Agreed.
can't accelerate.
And the Earth revolves around the
Yeah,
sun, and the
so-
sun around
So it's a purely theoretical, like, let's say, we don't have an example of a
Yes.
known for sure, like, inertial reference.
Well, there's two things. I mean, the answer is in principle is yes. There are a couple of things I can say to that. One of them is you have the same issue in normal classical mechanics.
Yeah, but I don't say it's like, it's just like.
But that's true. But also in classical mechanics, there's always something pushing on you. Yeah.
Yeah.
Only in the situation where you are the only person in the universe, so there's no attraction whatsoever. Then maybe then. But the most important thing is, what we now do is that we constantly take our inertial frames to be stuck to observers, and then you say, well, but the observers, their masses there has to be some acceleration if you compare them to each other. But what about the frame itself? So you can have an inertia, so you can have a frame that is accelerating, even if it is not attached to somebody in it. Do you see the difference?
Oh yeah, okay.
And that inertial frame, which is now highly theoretical construct because it is not attached to somebody, even though the people in the frame or the objects are accelerating, because non-acceleration again might be a very theoretical construct, hypothetical.
If they move with the same acceleration,
yes.
we have the same, like, will be an inertial. Okay. Okay.
All right. So, all clear? Okay. So now you know why we call this special relativity. All right. So, well, let's continue. This was somewhat out of what I really want to do. Where's the clever thing is they always look like a mouse, but they're
I think it's here.
all right, then we have nothing then.
Maybe somewhere around here.
Well, I'll just use this part of the board and we'll find out what happens if I run out of writing space, okay? Okay. So one resolution to paradoxes like this that you might have encountered if you looked at the exercise of last week was, well, not everybody was in an inertial frame. So it might be that if you did some calculations, you did your calculation applying special relativity to a non-inertial frame, and your answer is simply wrong. So if you did some calculation and you find that you don't understand why the number comes out differently than you thought, go back to the exercise. Now knowing about inertial frames, check whether you were in an inertial frame. But there is a second reason why answers might sound paradoxical, and that has to do with the loss of simultaneity. Now, do you know what that is? Just by the words alone.
Two events happening at the same time?
Yes, but there's a loss of that. Simultaneity means that if you have an observer in a certain frame, and that person sees two events happen at the same moment, then some other person in a different reference frame will claim that these two events are not happening at the same time. That is different than time dilation. Time dilation says if you know how much time there was between two events for one observer, you can calculate how much time, less or more, there was for the other observer. What I now say is that even if the amount of time is 0 between two people, two events for one observer, it might not be 0 for the other. There's no time dilation that can make that work, because if it is 0 for one person, then gamma times that will still be 0. So it's a whole new effect altogether. The loss of simultaneity. Now I will derive this today. And a second reason why sometimes results in your exercise in special relativity might look paradoxical is because you have not taken this effect into account. And I remember at least 2 people who sent me an email where they said, look, I calculated this and then I calculated such and I get a different number. And I wrote both of them back, yes, but you haven't taken into account the loss of simultaneity. Now, all of these exercises are for next week, because here's where the paradoxes lie. All these paradoxes you can solve by taking this effect into account. So it's important for us to now find this effect. Figure out how that works. Now, going back to the bigger narrative, if you remember last week we derived our 2 key results, time dilation and Lorentz contraction, by doing a thought experiment, a Gedanken experiment. Okay? And then I said, but this is not how theoretical physicists do it. It will be very difficult indeed with every single exercise you're going to do, have to first revert back to a Gedanken experiment to find how laws work. So what I'm going to do now is do relativity in the way that people actually in the field do it. We're going to find the exact same results, time dilation, Lorentz contraction, but this time without any of such experiments, and we're going to find the loss of simultaneity and the bigger relationships between durations and distances. And in order to do so, let's go back for a moment to normal 3-dimensional vector spaces. So what I'm going to write down, and this is where I start my lecture proper now, suppose that you have an xy space. Forget about relativity, forget about classical mechanics, forget about any physics. Just three-dimensional, I write 2 dimensions, easier to draw, but three-dimensional space. And suppose that I draw a vector there. Just some arrow points from the center, points to here. Doesn't necessarily have to be the center, but it's easier to draw. And suppose that the amount of distance in x direction of this vector we call delta x, and this amount we call delta y. Okay? So let's make it visual. Here's the center of my coordinate frame. This is x and this is y. And because I just happen to be looking at you, you're going to be my vector, okay? If you want to walk from here to him, one thing that you can do is say, well, you know what? Walk in a straight line under this angle. This is what you typically do if you point somebody to somewhere where it's a Vrijthof. You don't say, well, walk 50 meters, then take 90 degrees and then walk. You just say it's that direction, this many meters under this direction, yes? But in principle, what you can say is if I want to go from here to there, I say, well, I take delta x steps in this direction, and then I take a 90-degree turn, and then I do with delta y steps in that direction. This is how you get here. X, y. What is the distance from me to him? This distance?
Y squared plus x squared, and then the square root of that.
Yeah. It's just Pythagoras theorem, yes?
Yeah.
So you would write it like this. Now we call this distance, we call delta S, relativity. Okay, there you go. No relativity in principle here. Well, the only thing what we have is just your basic Pythagorean theorem in a Euclidean space, xy space. Now suppose I'm going to do something else. Okay, I'm going to take you and I'm going to put you in a different seat and I'm going to put you here on this seat. You don't actually have to visually do it, everybody just imagine him sitting there, there's no difficulty there. And suppose I'm now going to ask the same question where he is now, and let's draw that in red. I could have set him now here. I would have a different delta x and a different delta y. So let's put little primes to say that they're different. But suppose that I asked him to sit at the location that kept delta s a constant. He is not allowed to change his delta s. So that means from here he should have moved in a circular motion, agreed?
So it should be shorter. They should be closer to the y-axis, no?
Well, I mean, I didn't draw it on scale, but this is why I tried to say it in words. Suppose that this has the same delta s. So delta x is a different number, delta y is a different number, but delta s is the same number. And yes, if I was really smart, I would have actually drawn it that way to scale. But suppose that we did this, okay? Something interesting has happened. Namely, by placing him from there to there, he's still at the same distance. And I've gotten a little bit of extra delta x, but that cost me a certain amount of delta y. And they're related by the Pythagorean theorem. So that's very simple. Now suppose that I tell him that he can sit wherever he wants, but always only at a location that has a fixed delta s. He's not allowed to change his delta s. So that means he's only allowed to sit in a different position in a circular motion somewhere. Okay? Then wherever he's going to sit, by definition, means delta s has not changed, but his delta x and delta y have changed. Do you agree with that?
Yes.
Simple enough, yes? Now suppose that instead of asking him to go and sit in a different place, I'm going to do the following. This was my x, that was my y. You stay where you are, and I rotate my axis. So I went from my blue frame now to the red frame on the board. He hasn't changed, but do you see that he has now also changed his delta xness and his delta yness? Do you also see that the distance between me and him has not changed?
Yeah.
Because I haven't taken a step in any direction, I just stood where I was. The only thing is I rotated my two axes. Now everybody understands that me rotating axis will not have any influence on the number of delta s, even though it does have an influence on the number of delta x and delta y. So there's a law in Euclidean geometry. And the law is you're allowed to rotate your axis, not rotating, you have to rotate and then stop again. But at the moment that you've stopped, you will find that you have changed delta x, you have changed your delta y, but distances have not changed. So what I'm talking about really is There is an invariance of distance under rotations. I can rotate as much as I want, the distance will never change. Simple enough, yes? So in Euclidean mathematics, you have the law of the invariance of distance. Delta S will always stay the same number. Simple enough.
You're saying invariance, so
Yes. Invariance, if you recall from last week, means that if you go to some other guy's frame, then there is a number that does not change. In this case, that number is delta S. You go from this frame, blue on my picture, to this frame, that was the red picture. Numbers have changed, but not delta S. So delta S is invariant under rotating. So there's a law there. The law of invariance of distance. Here's the beautiful thing.
There's difference.
What, sorry?
I'm just saying. I'm thinking if we add
Yes.
just y, if we just do the traveling in triangular way,
Yes.
your whole distance will also be different. But just like more. Never mind.
Okay, well, if it comes back, do ask. Here's a claim. Suppose that this is not a location and that is not just a location. Suppose that this is an event. And you know what an event is? It's a location and a moment in time. This is also an event. A moment in time and a moment in location. Sorry, a moment in time and a location. So let's say that this axis is now not an x-axis, it's a t-axis. Amount of time. It's the same idea. It's just I've replaced distance by amount of time in one of my directions. Then you would say, oh look, that means I still have the same law,
Strange.
right? And maybe that hasn't changed. Maybe there is also a law in distance and duration between two events. That you can rotate through time and rotate through space in such a way that the amount of time and the amount of distance, the delta t and the delta x, do change. Delta t is not the same as delta t prime. Delta x is not the same as delta x prime. Or, well, it's still called y over there, but you know what I'm talking about. But some combination of these numbers has stayed the same. Delta s. This might sound familiar to you now. If there's one thing that we saw last week, is that in relativity,
Speed will be constant. It's the equivalent of the, I guess.
yes, and I will show you today where exactly speed comes in. If you look back at the exercise of last week, one thing that you saw was that if you went from one guy's observer frame, where he measured the delta x and delta t between two events, and you went to some other guy's inertial frame, and he also measured the different delta x and delta t, the numbers were different. Okay? Here's a claim. Suppose we say that nature will in a particular way make sure that delta s is the same number still, even if you go from one frame to the next. Do you see, just in my example with the delta x and delta y, that you can let go of a certain amount of delta y became smaller, but then you had to increase in delta x. One of them becomes shorter, the other one becomes bigger. Does it sound familiar to you if you talk about space and time? Did not we see that time became dilated and space became shorter if you went from one frame to the next? It's the exact same idea. Now, Einstein never realized it in this particular way. It was his mathematics teacher, Mr. Minkowski, who saw his former student Einstein's equations, relativity, the time dilation, the Lorentz Construction. So wait a minute, that's sort of like a vector of which the distance, the total distance should be invariant. And then Minkowski thought, that means that you can make this very graphical. We can write down this law that apparently encapsulates all of special relativity. Now what I'm going to do now is I'm going to write down the exact law, take that as our starting point, leave out our postulates of last week, and then rederive everything else. So I'm not going to teach you anything new. The results are going to be the same, but the starting point and how to get there is going to be very different. Let me just write down the law, and then we're going to do the derivations after the break. Okay? And here's where I have a lack of... what Well, that's all. Well,
Lack of space and time.
lack of space and time, apparently.
There's
Well,
a tissue there.
where is it?
Like
This thing?
Very quickly.
on the board.
Oh, this piece of wiping cloth? Well, that's all. Okay, that's all that we have. Okay. I'm going to write down the law for you. It is in fact exactly this law, but there's one key difference. And if you want to ask me why the difference is there, nobody knows, including me. I'm going to write down the law. Now you know the difference between small d's and big d's?
Yeah.
Okay. ds squared is equal to d squared dx squared, and let's make it three-dimensional. There's also a y squared and a z squared. There you go. So at this point it's just Pythagorean theorem in 4 dimensions, having included time. Here's the one key difference, that nobody knows why that is true. That minus sign. Now, why is that true? I don't know. Einstein didn't know. Minkowski didn't know. What we do know, and this was Minkowski's brilliance, he saw, well, if you write down distances in space and time, like Pythagorean's theorem with time, but with the extra minus sign, all of special relativity will come out. So this is a summary of all of special relativity.
So you just try empirically to see if everything works?
Yes, that's what you do. Yes?
So does that mean that this drawing with delta t on the x-axis is in fact wrong?
Yes, but it's very hard to draw what happens to minus t's.
Yeah.
And there is a graphical way to do this. It's called Minkowski space-time diagrams. And I'm going to show you some of that next week. But how to read and to draw these drawings where all of a sudden you have an extra minus sign in front of these things is an industry of its own. Because it's very, I mean, this is easy to draw, yes? But with the minus sign, things become much more difficult. And all of a sudden your pictures, you really have to study how to read these things. So right now I'm not going to do any more drawing. I'm just going to do everything algebraically. Next week I'm going to put it into graphs. Robin, you had that question too?
No.
I think so, okay. Oh yeah, Lizzie.
Yeah, I wanted to ask, are we going to keep the CS1 or are we going
No,
to
I'm going to
use-
put it in a moment. And actually, let's take that before we go into the break. If people look at this, they might say, wait a minute, something must be wrong here. Because, well, let's go to the unit system of meters. Here's a meter squared, there's a meter squared, there's a meter squared. Here's second squared. Now you cannot add second squareds to meter squareds.
Mm-hmm.
So what do you do?
Meters of velocity.
So there has to be a velocity somewhere, yes?
Yep.
Yeah.
Okay. Now, this is, forget about everything that you knew about relativity. Just by pure mathematical factness, you cannot add dt's to dx's unless you have a velocity squared here. Now, I'm going to call it c squared, but note I'm not stating that it's the speed of light.
Mm-hmm.
I'm also not stating that number is an invariant, which we took as a postulate last week. Forget about all that. I'm just saying, just for mathematical reasons, there has to be something with the unit of speed there. Why do I call it c? Well, I don't know if this is a speed that light actually follows. I'm just saying there's a speed there.
Mm-hmm.
Now, it will turn out later to be the speed of light, so I'm already just putting the number there. Yes?
But then shouldn't we add also a factor of speeds in the ds square thing?
No.
Because it came like in the formula. If you multiply something in the like, I'm just like thinking that we are adding. If we just say that without the c, it's just simply the Pythagorean theorem.
Yes.
Like, if we add something, don't we change the rules? So it must like kind of balance the thing. No, I don't know.
We're not changing any rules. Why are we changing rules?
We are multiplying a time by a constant, so we must find this constant in the results on the other side. No.
Well, first of all, the value of this constant is somewhat irrelevant. It's a speed, so that means it's a meter per second in our unit system. You can change that number by going to a different unit system, right?
Mm-hmm.
So you can the value of the number is in certain respect is irrelevant. Now, that there should be a speed again is just maths, and that's all that I'm saying. I'm not changing any rules. I'm just saying that add this, add that, add that. You cannot add this, therefore there must be a speed squared. That's all I'm saying.
So it's just like the unity that is changed.
It's the unit, yes. The only thing that it does is a unit conversion factor. And in fact, I want you to think about this thing at this point as such. Yes, if I write down c, you think about the speed of light with all its properties that you saw before. Oh, it's invariant, you cannot go fast in this number. All of these things I'm not assuming. I'm just saying there has to be something that changes the wrong unit to the right unit, and it has to be a velocity. I don't care about the value. I don't say that it's invariant. I don't say it's the highest velocity that you can attain. I'm just saying there should be a number there that changes the unit accordingly. That's all that I'm doing. Now, to show that this is the speed of light, that it is invariant, that you cannot go fast in this number, all of this is the work that we still have to go and do.
Okay, then we're assuming that s is a speed, but then if
No.
Here?
This is a meter squared.
Okay.
Meter squared, meter squared, meter squared, meter squared.
Okay, but then here also we have a so then also even in the first part we couldn't do it here.
No, but this is just me leading up to this story. So this is just me drawing a picture
Okay.
in x and y, then saying, well, apparently there's a law there. Apply the same law, and then
so
mathematics
here
says you
S
see.
is also in meter.
Yes.
Meter.
Yes. Okay. Any questions about this part?
So is that kind of just like a
Just
constant
seconds.
of... Sorry.
No, it is
Kurt
handled,
is handled. Yeah, just a quick question. The minus follows from the mathematics, or you just...
No, the minus doesn't follow from anywhere. So the question is, where does the minus come from? Nobody knows. The only thing that Minkowski realized was if you put the minus there,
Then it works.
then you ultimately make predictions, then you find that this works. So I'm going to take this as a postulate. Now, you know, every time that you're going to build a physical theory, you have to start with your postulates. This is what I'm going to assume that nature does. What Einstein did, that we saw last week, Einstein himself wrote in his 1905 paper, my postulate is going to be the speed of light is invariant for all. Okay, and there was the second postulate, the principle of relativity. What I'm saying now is that Minkowski realized, throw away that postulate about the invariance of the speed of light, replace it by this one, and you'll get at the exact same result. So if you ask, but wait a minute, aren't you just building in a postulate? Yes. We're just replacing one of the postulates by Einstein by a new one. And now the work that we have to do is show that it's the same thing.
That implies the postulates are the same? Are saying the same thing?
Yes, and I will promise you by the end of today's lecture of the second half, we will have shown that this automatically says that the speed of light is indeed an invariant. So do you see where this is going? We've replaced Einstein's postulate, replaced it by Minkowski's postulate, going to work through the mathematics, find the same results as last time, so that proves to you that it's really the same theory, and then I'm going to show that Einstein's original postulate was really just built into here. And that means that this is really equivalent to what we started out last week. That's our plan for today, for the second half. Okay? Alright, so let's have a break.
Move the computer a little bit.
You see.
Alright,
End of next
everybody.
Getting there.
We're at the point where we're actually going to do some calculations. Let me just re-emphasize one more time. We started with Einstein's postulates. I wrote them down. Those were the upper two that we discussed last week. And the claim that I'm now making is that if you replace this one by this one, you leave the second as is, but if you replace this one by that one, you will find the exact same theory without having to specify anything about light. What we will find though is that if you then go through the calculations, you will find special relativity again, including all these properties of light that in our first derivation had to assume, and we're going to find, from here, we're going to find this one back. And that tells you that these things are really just different packages of the same thing. Now, I always said that this is the way that theoretical physicists use relativity, and this is the way that we're going to apply it for the people who are going to follow those courses in periods for electrodynamics and general relativity. So, let's go through this. How are we on this? It's going to be a principle, a postulate. Why the minus sign? Nobody knows. So what you do, you take it as a postulate, just like in Einstein's time nobody knew why this was true. But you take it as a postulate, you do the calculations, compare it to nature, and this is what nature apparently does. Alright. So here's the whole thing. Apparently it's like Pythagoras' theorem, but the amount of time between two events comes with a relative minus sign. That's all there is to it. Now this by itself is not yet a law of nature. This is just me adding squares of numbers. it becomes a law of nature at the moment that you tell what this thing does. Now what does this thing do? And that's exactly this postulate by Minkowski. This number is an invariant. You can go through any other system that you want, the number will not change. This number will change, that number will change, that number will change, that number will change, but this particular combination will stay the same. This is exactly like the thing that we did with persons sitting from one chair to the next chair. Their distance will not change even though their delta x's and delta y's will. Just like we had this law in Euclidean geometry, we have a law apparently in nature, special relativity. Nature has decided that this particular combination is invariant. Yes?
Under what transformation?
Lorentz transformations.
Okay.
And this is exactly what we're going to derive today. In fact, you are going to during the tutorial. So,
why does it say invariance of dt?
Yeah, that's because depending on which author, which lecturer you listen to, some lecturers take ds squared as the number that is invariant, but there are also lecturers, and I'm one of them, that prefers to take this number, d tau. D tau is defined, it's just a definition, c squared d tau is minus ds squared. It's just a definition. Now why do I do it like this? Well, let me first write down what it will look like. Well, if this is just minus that, then all of this should just adopt an extra minus sign overall, yes?
Okay.
So this is just really the same statement all over again. And why do I choose this particular version, not that particular version? Is because it agrees more with the narrative that we're following here. So, but you do agree with me that if d tau is an invariant, then c squared minus d tau is also an invariant, yes? Okay, so this is going to be our starting point. The fact that this thing is invariant is our new postulate. So again, without this part equals invariant, you haven't written down a law of nature, you've just written down a particular sum of squares of distances and durations. The fact that it's invariant, this is what makes you, that gives you relativity. Now, let's do some work. I call this d tau, and you already know something that is called d tau.
Time dilation, the proper time?
It's the proper time. My claim is, what you saw before as being proper time, d tau, is actually this number. How can you tell? So you have two things happening, two exploding firecrackers or something. How can you tell that d tau is the proper time?
Oh,
Go ahead.
because before, if we want to calculate d tau by definition, the event must happen at the same location. So dx to the power square is equal to 0, dy to the power square is 0, and so on and so on.
Very, very much agreed. It's completely correct. So for everybody, this d tau is what you called the proper time before. If you recall from last week, proper time meant the amount of time that passes between two events for the observer who sees the two events happen at the same location. Right? That's just the definition of what d tau is. Now, if there's one defining characteristic of seeing two things happen at the same location, that means that the distance between these two events, the spatial distance, should be 0. Agreed? Okay. So you have two exploding firecrackers. There's one here, bang. A couple of seconds later, that's dt. It explodes again. Second one explodes. Two events, but they both happen at my feet. Now that means that dt, as seen by me, is going to be those 4 seconds. My dx is going to be 0, because the spatial distance between the first exploding firecracker and the second is 0, and the dy and the dz, all of them 0. Agreed?
Mm-hmm.
Okay. What if the firecracker, the two firecrackers were exploding here while I was standing here? So it's 3 meters away. Well, it is a little bit less, but say 3 meters away.
Because it's the difference that we are.
Exactly. Just to make sure that you understand the difference between location and distance. If my two firecrackers were both exploding here, 3 meters away from where I am, then the first exploding firecracker will be at x is 3. The second will be x is 3, so the dx between them would still be 0. So you don't actually have to see the two things happen at your origin of your reference frame, but it has to be at the same place in your reference frame, wherever that is. Now, if you have your two firecrackers exploding at the same location, then this is 0 by definition, this is 0 by definition, this is 0. So in that particular case, you will find that c d tau squared is c squared dt squared, because the rest is 0. And as a result, d tau is exactly dt. Conclusion, what is d tau? D tau is the amount of time that passes for that one observer who sees the two things happen at the same location, what we call proper time before. So let's write that down immediately. This is called the proper time, just as we had it defined before. So now you know why we call this d tau. I hope now you also see now why I prefer to work in d taus and not in ds's, because we had already defined d tau, so we can relate back to what we saw before. Okay, good. Second question. Suppose that the two firecrackers explode, but I'm now going to do it in a frame that is moving with respect to the two exploding firecrackers. So they're both exploding here. Yes? But I walk along now in a different frame. So let's check what happens, okay? So where the chair is an exploding firecracker. I walk past the thing. Okay, so there's a pang. I've chosen my situation that it happens at my axis 0 in my walking frame. I walk along and then the other one explodes. Okay, second pang. Is the x 0?
Is
the x? It's not 0, yes? In my frame that is attached to me moving along, the first exploded at position 0. And here it will be at position -2 or something like that. Will be different number. But do you now see that if for the other person the x has gone from 0 is now -2 squared, then something must have happened here. Because the outcome should still be the same number, agreed? Because that is that law. That is the principle of the invariance of d tau. So let's see what happens if that works. So again, two observers. Observer 1 is in the reference frame where the two events happen at the same location. And for that observer, we have found that d tau is just dt. This is what we did before. Here's a second observer. That was the walking guy. That was me. And they do not happen at the same location. Now, in my example, I said the distance is now -2 or something like that. Let's do away with the number. This is called delta x. Okay? So the two events do not happen. At the same location. Now, it is practice in relativity to really make sure that you understand by looking at the coordinates, whose coordinates you're looking at. Now, you typically do this by putting a prime there or something like that. Okay, so let's do that. The x prime is the person walking with respect to the two exploding firecrackers. The x is not 0. But then by the invariance of this thing, the fact that this number has changed must mean that this number must change accordingly. And we're going to find out how much this number must have changed. How much time there must have been dt primed as seen by the person who was not seeing them explode at the same time. And you can already guess that this will give you time dilation, yes? Yep. But let's see if we actually get this out. So the question is, what is dt primed then for this guy? And it's certainly not going to be dt. What we're going to do, we're just going to literally write out the invariance. Now, just for notation of gravity, let's do away with the dy in the dz. Let's assume that everything happens in this motion, so we don't have to worry about dy. We're going to use a reference system in which the two exploding firecrackers happen at the same y and at the same z for both observers. Okay, just you don't have to. You're free to put that in. It's just more writing. So we're going to put dy and dz 0 for both observers, and I'm going to write out this law. So what we have is c dt squared minus dx squared, and again dy and dz is going to be 0, must equal, and this exclamation mark is this law, must equal c squared dt prime squared minus dx prime squared. That is the law. Now we know that this number is 0 by definition. So c squared d squared is c squared dt prime squared minus dx prime squared. This is what you get. So I'm just applying the law now. Now we're going to do the algebra. So physics is over now. I'm just going to do some maths. You know what? Let's divide both sides by c squared. As long as c, whatever the number is, I have never said that it was the speed of light, it's just a number, but as long as it is not equal to 0, I can divide both sides by c.
So just why do we get rid of the gx square?
We didn't. Oh, this one, because by definition, they have at the same location.
Okay, yeah.
Yes. So the whole left-hand side is observer 1, and the whole right-hand side is observer 2. Okay, so I divide it by c squared. What I can also do, if I so want, is, you know what? I am also going to divide you agree with this step? Just maths. No physics. Look what we have here. We have a dx, amount of distance, divided by the amount of time. That will be a velocity, yes?
Yeah.
Now we can call that velocity v if we want, because really this is just a velocity. But we have to be a little bit careful right now. By the way, it's velocity squared, because the whole thing must be squared.
Okay.
There was already a c squared there. So I get this. Is this what you get? Question. What velocity is this? It is a velocity, but what, I mean, can you point it out in our visual situation?
It's
You're traveling.
the amount of time.
Yes.
The amount.
That's right.
The distance you move.
Yes.
The distance you move divided by the amount of time. It's just
Yes.
for the two events.
That's all there is to it, right? I mean, it's my amount of distance, dx primed, divided by the amount of time that I measure that this takes. That's another way of saying how fast apparently I am moving with respect to these firecrackers. So it's really just v, the velocity with which these two reference systems are moving with respect to each other. So v in this example is really the relative velocity between this person and me. So it really is v. Now then we end up with a very beautiful equation, because what we see here is that d squared equals 1 minus v over c squared, square root, not square root yet, dt, prime, thank you, and there's a square still. And then we can relate these two times to each other. We can say, okay, in that case, dt primed equals 1 minus v over c squared dt. Does that look familiar? Do you remember that dt in our situation was the proper time? Does look familiar? This is exactly time dilation that we derived before. And the only thing I've used is this law. What I have not used is that there is a speed, that there's a light ray bouncing up and down a train cart or something like that. I have not used how I measured the thing. As in, well, I was standing over here and then somebody shouted me the information. I just only used the property of space and time itself. No experimental stuff is in there. Sure, for visual aid, I took an exploding firecracker, but it's all that I did. That's very different from the derivation that we had before, in which we had to say, well, there's something moving here, and then we do this, and then we have a mirror over there. I took away all the stuff of the experiment, and I still get the same answer. This is why this derivation is preferable. It's completely devoid of experimental details, so therefore whatever comes out must hold true for everything. Do you remember last week when I said, when we did the derivation using a Gedanken experiment, that I said, well, the crappy thing about that derivation is you've seen this equation come out of this particular experiment, and then you promote it to general validity. Nothing of the kind is happening here. I never put any experimental situation in the first place, so therefore the outcome is general. So it's an extremely important result. We just find time dilation one more time. So, apparently, this postulate gives you at least some of special relativity. Let's see if you can find some more. Now, you can already guess the Lorentz transform, the Lorentz contraction is yours to try, but maybe you can already sort of think of how you would do that. Any idea? We're not going to do it in full. This is your exercise for the tutorial. But how, if you have only this law, how would you find out whether lengths are going to be the same, right?
Take one observer for which two events happen at the same time, and one for which they don't happen at the same time.
Sure. Then you get the formula out. But why would you take the two events happen at the same time for one observer? And it relates to something that I've mentioned to both tutorial groups on Friday. If you measure lengths, but you want to measure the length of something that is moving, you have to measure the front end and the back end at the same time, yes? So that means that one of the t observers will have his dt set to 0 and the other one's not. Put that in, work it out, you get Lorentz contraction. There you go. No experimental details, the only thing you're saying is whatever you do, no matter how you do it experimentally, you have to measure front end and back end at the same time, and then you find Lorentz contraction. Now, this is for you to work out, but we've mentioned a couple of times that there is a bigger set of durations and distances between the two observers. Not just this one and the Lorentz contraction. You can ask yourself the following question. Can I erase this, by the way? I need some space. You can ask yourself the following question. We have found now one relationship between one person's duration and the other person's duration that apparently obeys this rule. And if you have done the Lorentz contraction exercise, you will find that you've now found a second law that obeys this rule, a second relationship between dt's and dx's. What I'm going to write down now, I'm just going to give it to you, and it's up to you to prove that it is correct. I'm going to give you the full set. All possible relationships between this person's time and this person's duration and this person's time and this person's duration for every single situation possible, as long as you stay within special relativity. These are called the Lorentz transforms, and I'm going to give it to you now, and if you feel, wait a minute, I want to know where it comes from, that's for you. Here you go. Lorentz transforms. You take one person's time, and you want to know, right? And you want to know how you can calculate this amount of time between two events happening. If you know the other person's amount of time, what you do is this equation. I'm just giving it to you right now. You have to show for yourself that this is true. So there's the two exploding firecrackers. One person says that there's 3 seconds in between. dt is 3. And he says, and in my frame, the amount of distance between the two exploding firecrackers is 5. dx is 5. How much time does it look for the other observer to see the two firecrackers explode? You take this guy's 3. You take this guy's 5. You multiply it with the relative velocity divided by z squared, add it all up together, put a gamma factor in front, and you get how much time there was between the exploding firecrackers by the other guy. Now, that's not all, because you can also ask, well, how much distance is there for the other guy? So, if I see them explode 5 meters apart from each other, how far apart do the firecrackers explode for the other person looking at it? It's almost the same equation, but not quite. What's this?
Just prime is for
One of the two.
Which one of the two?
Depends on your situation.
Okay.
So if you have to give me a situation, I will tell you which one is the prime to which one isn't.
So just again with the firecracker, for example, one guy is moving towards the firecracker and the other one is like on the reference.
That actually relates to my next point. So I'm going to take your question related immediately to the next thing. Because really what he's asking now is, okay, I can calculate now the amount of time and space as seen by one person to the other person. What if I want to calculate back? Okay, there's two ways you can look at this. You can say, well, you know what? This is two equations in two unknowns, namely dt and dx. And if you know your maths, then you know that you have two equations, algebraic equations into two unknowns. You can solve the system and find dt, not primes, but dt and dx in terms of the primes. It's a mathematical exercise you can do. So if you do that, you will find the answer. There's a second way of looking at it, much more physical. Note that I put the plus minus v here. Can you tell what that means physically?
It doesn't matter if you're going backwards or forwards.
Well, it does matter because sometimes you add something and sometimes you subtract something.
The direction of the speed?
And yes, I mean, are you walking in this direction with respect to each other? Are you walking in that direction? Now, suppose that I'm walking in this direction. Let's say that corresponds to the plus sign in this equation. Okay, plus sign. And then I take my time, calculate this guy's time. Now, this guy wants to do the same exercise. He wants to take his time and calculate mine. Now, as seen from his frame, what happened to the v? That comes with an extra minus, agreed? If I walk with 5 meters per second with respect to you, then you see me walk with minus 5 meters per second in the other direction. Agreed?
Yep.
Yeah.
All right, so you can already sort of guess that it's probably the same equations with all the minus signs reversed. Now, if you do the mathematical exercise, you will actually find that that is the case. If you do the maths, then you find that this is really true. So, if you want to do the opposite exercise, you know this symbol, yes? It just means whenever there's the plus here, you have to write the minus there and the other way around. And you get the same type of equation. It looks very much the same. The only thing that has happened is that pluses and minuses have reversed. This is wrong, excuse me. X dt primed. So you can go in both directions. So you can go from one, go to the other. Now, if you have to start with the plus or the minus, that is an exercise-dependent thing. And you have to figure it out with every exercise. So, you will find exercises later where there's one person looking at two events, and he says there's so many meters between them and there's so many seconds between them, and you have to calculate how many meters and seconds are there as seen by the other person. Just fill out these formulas, you will find the answer. These are called the Lorentz Transforms. And in the tutorial, I'm going to ask you to put these numbers in here and really show that it will give you an invariant. That apparently if you replace all dt's by this and all dx's by this, and you then go through the math, then ultimately you will find the exact same expression with all t's replaced by t primes and all x's by x primes. You will have found that this has been an invariant. That proves that this is really a general set of rules. But that's for you to go through the maths. Now, well, if this is the most general set, by the way, is it the most general set, or can you think of another? Can you think of more? More relationships between times and durations and distances that leave this invariant? I mean, I claim that this is the full set, that there's no more than this. But maybe you can think of one or two? No?
Maybe with acceleration?
Oh, acceleration makes life
dt over
difficult.
dt over dx or something like that.
Let me go into the acceleration for a second. Yes, if you go into acceleration, and we now know that brings you into, if you're not careful, into non-inertial territory, that means general relativity applies, and then you find that the rule still holds. But all of a sudden you get extra numbers in front of these. You have to take into account the extra numbers. Where these numbers come from, that is general relativity. So I'm going to leave acceleration out for a moment. How about if I replace all the x's by minus dx? So that means I'm still in the same reference frame, but instead of this being my plus x's, this is going to be my plus x's. Doesn't matter, right?
Well, the same.
This is called parity in particle physics. You replace all x's by minus x and all y by minus y. So in principle you can do that if you want. Here's another one. Suppose that I have two observers. Here's one person seeing the two firecrackers explode at his feet. And here's another observer standing still with respect to the firecrackers, but 3 meters away. We already discussed that the dx then will not change. So apparently that is also possible. Agreed?
Why wouldn't it change?
Because if the two firecrackers explode over here, and I'm now standing here and it's 3 meters away, the first firecracker explodes at 3 meters, x is 3. The second also at x is 3. Their dx is still 0.
Oh, right.
So you have some more rules here. You can do parity, that means just switch all x's by minus x. Then it still works. Then this is still invariant. And you can have, as we call them, translations.
Yeah.
Literally just stand a couple of meters away from where you're originally standing and it still holds. But physically this is no surprise, is it?
No.
I mean, the amount of firecrackers, it takes 2 seconds between them to explode. And I go stand over here and then watch them explode, it still takes 2 seconds. Me having stood a couple of meters away from the thing will not change durations. So these are sort of trivial relationships. So, where things really get interesting, where you get your relativity in, is when you try to put time in space. Now these are called Lorentz transforms. In some books you will find them called boosts. Why? Just because? Because, well, if you think about it, what you do is you go to another frame that moves with respect with v to your original frame, yes? This is what you do when you go from one to the next using Lorentz transforms. So you're boosting to another frame that is moving with respect to where you came from. This is why it's called a boost. How do I get, if this is the general set of durations and distances, how do I get time dilation out? If this is the most general one, then I should also have my time dilation in there. Can you tell how? It's a very easy question. Under what condition are you allowed to use time dilation?
Same location.
Same location. So what does same location mean in mathematical terms? Okay, so that means that this is 0. There you go, time dilation. Lorentz contraction, same thing. If you want to measure something, then you have to make sure that you measure front end and back end at the same time. So what do? Work through math, you get your time, you get your Lorentz contraction. So this is really the most general set between the two observers. Whereas Lorentz contraction time dilation required the observers, at least one of the observers, to be very specific, either measure things at the same time or measure things at the same location. These do not. You can always use these.
Mm-hmm.
And that brings me to this moment, this thing that we discussed at the beginning, that one thing that might have gotten you into trouble with your exercise and your paradoxes. One of them was that maybe you've done your calculation in a non-inertial frame, and I mentioned there's a second one. Maybe you didn't take into account the loss of simultaneity. So let's look at that. So suppose you have two observers. One observer sees two things happen at the same time. Okay? So there is simultaneity. For this observer. Okay? And then there's a second person looking at those two events, asking, okay, so how much time is there in between these two things? Can you see that it will not be simultaneous? Non-simultaneity, simultaneity. There you go. How can you tell? What does simultaneity mean in mathematical terms?
They occur at the same time.
Yes.
Same.
So
dt is 0.
dt is 0. Okay, good. So that means dt is 0, yes? Put this dt to 0.
Yeah.
Okay. Then you get a non-dt for the other guy. And what you see is that how much the other person sees the first person's two events not being simultaneous is dependent on how fast he was moving with respect to the first one, but also how much distance the first person saw the two things different from each other. Let's make it specific. I have my two exploding firecrackers one more time. There's one observer who sees one firecracker over here, but this is why it's different from normal Lorentz contraction or time dilation. He sees the other firecracker explode a little bit away from him. So one firecracker is here, the other firecracker is there. And he stands over here, and for him both these two firecrackers explode at the same time. But there is a distance in between. There is a certain amount of meters. Let's say make it 3 meters. Bang. But they happen at the same location, okay? Same time. Then some other person comes along, and he is going to see whether these two events also were simultaneous. Now, just by time dilation, you would think, oh, but wait a minute, the amount of time must be different, but there was no amount of time because it was 0. So you cannot use your time dilation formula. So your time dilation will not help you, but these will. The only thing you have to do is to know how much time there was in between the two exploding firecrackers as seen by the moving guy, the guy who's moving with respect to the two things, is take how many meters there were for the first guy between the two, that gives you your delta x, multiplied with how fast you were moving, multiplied with gamma. That is the amount of time that the other person sees between the two exploding firecrackers from his frame. Something very interesting happens there, because apparently things do not happen at the same time anymore. I mean, isn't that strange? At some point you can wrap your head around the idea that, wait a minute, I'm okay with things happening at a different pace. Things go slower if I look at a different thing. But at the very least, if that person sees two things happen at the same time, I also see them at the same time. That still is upheld. That is not upheld. That is also out of the window. Durations are different. Time dilation. Distances are different. Lorentz contraction. But also whether things happen simultaneously or not is also different. Now, if you go back to some of your exercises in case you came across paradoxes, and yes, next week is all about resolving them, but maybe if you want to already encounter some of them and you want to go through them. If you go through your paradoxes, I want you to check, first of all, did you do your calculation from inertial system or not? If not, that was your problem. Second, did you take into account that what happened for one person at the same time did not happen for the other person at the same time? Yes.
So, for example, when we use the example with how slowly someone will age,
yes,
actually it's not totally correct, because we can also say, oh, but the event of like aging is also different. It's not like, so if I'm like aging on 1 year, it won't be like simultaneous either. I mean,
there is a loss of simultaneity there. That is true, and that is aside from the acceleration thing. That's another way to resolve the twin paradox. But again, to work this out in full, this is for next week, right? Because there is some difficulty here. I will say this one thing. Remember this exercise that we did with the spaceship that went from one planet to the next? Well, at the same time, light arrived there. Do you see that there's an issue there in the question? Oh, the light arrived at the same time as the rocket.
Yeah.
The same timeness is not for both observers the same.
Mm-hmm.
So if you did that calculation, you found, wait a minute, there's something wrong here, and I knew that some people said already during the tutorial, wait a minute, there's something is off there. This is what is off. Okay? Again, the full analysis we will do next week, but keep in mind that this issue is there. Now, if you will indulge me for a couple of more minutes, I want to show you that these result in these, and then we've made full circle. Okay? Are you okay with that? Rodrigo, by the way, this is what I emailed you.
Yeah, I know.
Okay. While I'm wiping this, Rodrigo and some other people sent me a question. They said, wait a minute, I did the calculation with the rocket going from one planet to the next, and then you calculated from from the sun and star frame it took 75 years, but from the rocket it took 45 years. And then what he did was, okay, but I can also take the rocket and then calculate back how long it should have taken at the sun, and then it comes to 27 years, because there was another gamma there. So apparently if you calculate everything back to the sun, if you started with the sun, you got 75 years. If you first calculated to the rocket, and from the rocket then back to the sun, you had 2 factors of gamma, you got 27 years. Well, you would expect to get your 75 back again. And then as Sandros Rigo, again, next week we'll do this in full, that if you would calculate that the clocks at the star and the sun were not simultaneous, but from the rocket frame they were off by a certain amount, by that amount that we just derived, and you do that calculation, you get 48 years, which is exactly the missing part between 27 and the 45 that we had before. You get your 75 back. Now, if you're not following this, next week. Just saying, here's the resolution to one of these paradoxes. Okay, let's finish this lecture by showing that we are indeed back at our original postulate. What I'm going to do, I'm going to look at something that is moving with respect to me. Okay? Let's make it definitive. Let's say it's a flying microphone. Don't ask me why it flew and who threw it and all that stuff. It just is. Okay? Now, I want to have a velocity. I want to measure what the velocity of the flying microphone is as seen by me. Okay? Now, it's not going to be V because I'm going to reserve the letter V for the other guy's frame. So let's call it, for lack of a better word, U. So, with a flying microphone, one observer, that's going to be me, is going to look how fast the microphone is flying. And the only thing you have to do is measure how many meters the thing flies in how many seconds. Now, regardless of how I measure that, I've done the measurement and I find that U, how fast the microphone is flying as seen by me, is going to be the amount of distance I see the thing fly divided by how many meters, how many seconds that took. What are my two events? The microphone being here and the microphone being there. That amount of distance divided by that amount of time that it took as seen by me. Okay, that's good. 2. Some other person is also looking at the flying microphone, but that person is not flying along with the microphone. He's flying with respect to me. Maybe faster than the microphone, maybe not as fast as the microphone, but with a certain velocity with respect to me, that number is going to be V. Now, for definitive sake, let's say that it's a smaller number than U. Okay, so there's a microphone flying. Some other guy is moving along with the thing, but not quite as fast as that thing. Then you see that the microphone to him is still having a velocity. That velocity is going to go W. So the velocity W is how fast the microphone is flying with respect to the second guy, who's moving along with it, but not quite as fast. He wants to know how fast the microphone is moving, does a measurement. He says, you know what, I'm going to take how many meters the thing has flown, as seen by me, dx primed, divided by how many seconds that took, as seen by me, dt primed. Do you all understand the setup here? Okay. Now my question is, how are you, the velocity that this guy sees the microphone flying, how is this guy's velocity related to the other guy's velocity with which he sees the microphone flying? That is my question. How are U and W related? If this was non-relativistic physics, life would be very simple. Agreed?
Yeah. Just abstract.
You just subtracted 2 numbers. Yeah. Well, if the microphone is flying with respect to you with U, and you and I are flying with respect to each other with V, then the microphone is flying with respect to me by U minus V.
And W.
No, the W will be U minus V.
Oh, okay.
Yes. That will be normal physics. But we're not in normal physics because we know that dx's primes and dt primes are related in a very different way in relativity. So, we're just going to put this in. We know what delta x prime is. We know what delta t prime is. Those are given by these 2 equations. So let's just put those in. If I do that, just mathematically speaking, what I'm doing is I'm expressing the other guy's velocity with which he sees the microphone fly in terms of my dt and my dx. So let's just do the math. dx primed, there you go, it's gamma. dx plus or minus, which of the 2 is it going to be?
Plus.
Plus or minus? Well, I'm going to write it down. You ponder it. And so that's my dx prime, divided by the amount of time that he sees it, which can be expressed in my amount of time by this equation.
Is your amount of time going with the microphone or your...
I don't know what you mean by going with the microphone.
Where is your frame of reference?
It's here. You see the microphone fly over there.
Okay.
Why is it minus and not plus?
What's the difference?
Because for me, it's like if I am the one seeing the microphone moving and the guy is also moving even slower than the microphone, like the speech is...
Well, we can think about it right now. Who sees the most the X? Is it the guy who is walking along, or is it the guy who is standing still?
Standing still.
That guy sees the most the X, agreed?
Yeah.
Because that amount of space that he sees in between the two events is going to be a big number because he's standing over there. The guy who's walking along is going to be a measure a smaller number between the two moments.
Yeah.
So this is why it's minus. It must be a smaller number. This is why I put the minus. Remember that I said both of them work, but you have to figure out per exercise which one you have to apply. This is what I did now. It's going to be the minus. Now from this moment on, this is just going to be mass. Now, there's a gamma up and there's a gamma down. Cancel. No, you can because they're not zero. Gamma is either 1 or bigger.
Yeah.
So you can divide these out. What else? Well, I can, if I want, I can take a dt out here. So I get dx dt minus v. And here I put the dt out. Do you see that? Again, it's mass. Same thing here. I can get the dt out if I want. Then I get 1 minus v over c squared dx over dt times dt. Again, no physics, just going through the algebra. Now what do I do with the dt's here? Up and down? What do I call dx over dt?
U.
Our v's in u's. Which one is it?
U.
It's going to be u. V is the velocity with respect, the two observers are moving with respect to each other. V is not a statement about how fast the microphone is flying to either of the two observers. But dx was how many meters the microphone flew in how many seconds. So dx dt is going to be the velocity of the microphone as seen by me. We call that u. You get u minus v. Look at that. That sounds familiar. If this were Newtonian physics, we would be fine. It's not. We have to divide by something. Here's where the relativity comes in. 1 minus v squared dx dt is again u. So we get to our final expression. This was w. We find that how fast this guy is seeing the microphone fly with respect to him is not u minus v. It's u minus v divided by a number. U minus v divided by uv over c squared. So velocities apparently follow a very strange rule. Yes?
The v is the velocity with respect to what?
To the two observers, their frames.
So the u is the velocity of the microphone with respect to observer 1.
Yes.
W is with respect to observer 2.
Agreed.
And
Yes. V is the velocity of the two between the two observers.
Oh, okay.
There you go. Do you see that this is a very small number? The uv over c squared? If either the microphone is not flying very fast, or the two observers are not flying very fast, u is small or v is small, then this uv over c squared is going to be very small. You get this, you get Newtonian physics back. If either the microphone or the two observers are flying very fast, you get this. Final step. You promise to indulge me. Fortunately, we can do that. We shave this off the tutorial if that's okay with you. Okay, because I really, really want to show this. I promise that we get there, and we're going to get there. So this is just fact. This is what relativity does. Suppose that we replace now the microphone by something that is moving with c. I never said it was light. I never said that this thing was light. But suppose there's velocity. Suppose that somebody flies with that velocity. What do I do here? I'm going to apply this rule to that situation. What do I do? I'm standing over here. I'm looking at something that moves with c. I'm not saying that it's light. Something. Something moves with c. Which of these variables is going to be c?
No, u is c.
U, yes. U was the velocity of the microphone with respect to me. And I'm going to say the microphone I'm going to replace by something that moves with the speed of light.
But w is also c.
But why?
Because of invariance. You go the other direction now.
Yeah, I told you, forget about that rule. I'm going to show that that's the case. Okay? We replaced the invariance of the speed of light by this postulate. And I'm now going to show you that you will get your rule back. So let's do it right now. The microphones fly with the speed of light. So that means u is equal to c. That means that my w, I'm just going to plug in v of u is equal to c, gives you c minus v divided by 1 minus cv over c squared. Do some algebra. Just algebra, no physics. I took a c before brackets. It gives you this. Here I erased the square of c with this c. You will get this.
But how do you know that both c's are the same? Because one comes from these equations. Yeah. Well, you assumed that this was c, but you didn't say it was the speed of light.
No. What I said was there has to be a velocity. I call this c. Never said it was speed of light, but there is a velocity there. Okay. Then I say, still not specifying that it's light. I'm just saying I'm going to throw my microphone with this c.
Okay. Yep.
Then you go through the thing and you find, oh wait a minute. But then apparently, if somebody sees microphones fly with this particular c, then the other guy does as well. It just comes out of the maths. Or if you will, directly from the Lorentz Transforms. Or if you will, directly from this thing. Yes. Also note that the value of phi itself was of no consequence. This drops out regardless of what v was. It doesn't matter how fast the two people were moving with respect to each other, you will always find this. No matter what you do, if somebody sees something fly with c, then everybody will see that happen. Yes?
Then if we don't specify here c as the speed of light,
yes,
shouldn't we say it's also v then?
Unless you understand the question.
I'm just like confused with the c part that we add. That is just only I get that it's only for unity, but then yes. if we use the c, why do we use it in the formula then? If it's only like for unity and we don't specify anything about.
No, it has a value.
But what value?
You only say that it's the same c that appears in the Minkowski line element.
Yeah, so in Minkowski there is a value.
Yes.
It's
now if you're the only thing I've done now, I've said there is a c here, and I only said I'm now going to throw the microphone with that c. I haven't said what the value was. If you want to know what the value is, you do a measurement. You throw some microphones around. Ask one guy to measure how fast it goes, get a U. Ask the other guy how fast it goes, get a W. Put it in this formula and then get back what apparently this very particular value of C was. This experiment you do, and then you find that it's the speed of light.
Nothing about this shows that it's the speed of light, right?
Nothing. It just says that for mathematical reasons there must be a velocity in there somewhere to get the units right. And then given that that is the case, then apparently this is a very special rule, because apparently if somebody flies with that unit conversion velocity, then everybody else does as well. If you want to know what its value is, then you do the experiment. It might very well be that nature had chosen a path where this number existed, but just nothing happened to fly with that velocity.
It sounds a bit arbitrary to just like don't know, add velocity just to the thing. Like if I have a formula, you say, oh, I want it to fit, but I want to add like, I don't know, mass. I can like I don't know.
Well, you only add velocity because there's a time factor in there,
Yes.
and there's some distance. So
Yes.
Yeah, but how can you do it? Like, I mean, if you it's just like how could you first think about that relation? Like, because I get the point when you draw the thing about like the
Yes.
Pythagoras thing, but then initially we shouldn't be able to use that kind of relation then.
Well, historically it happened the other way around. Yes. We knew special relativity, then Minkowski found out that apparently it's equivalent to having assumed this. I mean, if your question is, why would somebody write it down in the first place? Well, that's a good question. Who would think of that? Well, nobody probably. It's in retrospect that we saw that it fits.
And why did you choose U instead of W to represent C?
I could have done the same thing. If I would have taken W to be C, I would have done the same. You would find that U must have been C.
Okay, so it is.
Yes, completely.
But there was no specific reason that you should choose U or W. Just
No, in fact, you can do it. What you can also do is take this rule and write down, well, then what is U in terms of W? And you will find that it's this. And then you would
redefine the.
and if you would take a W to be C, then you'll find that U is C, so it works both directions. Okay, people, thank you for indulging me. We'll see each other at NBD, yes?